Okay, hello everybody. This is the second attempt at recording this. I did 24 minutes yesterday and was told by a student that there was no audio. So thank you to that student. And here we go on the second one. So what we're going to look at today is really graphical properties of exponential functions. I'll come back and do these warm-ups at the end because this is something that we did a little bit earlier, but I want to go through a couple examples just to solidify that. So let's go to, these pages to get through. Sorry, let me just erase this. I thought I had erased all the notes from the last time video with no audio, but apparently not. All right, so first thing, right, our general form of an exponential function is going to be a times b to the x. Okay, this is without any transformations or anything. The initial value, right, is going to be a, and we're always going to look at an a value, greater than 1. Greater than 0. Can't speak. And the b value, there's really two cases. B can be 1 or B can be between 0 and 1, okay? And so there are different cases, but the key thing here is that B can't be negative. If B was a negative number and we're raising it to an exponent, it's going to jump back and forth and it's going to be positive or negative, so it won't even produce a continuous function. Here's the picture, right? When we have a positive a and b is greater than 1, so that's growth, right? So when we have a base that's bigger than 1, left to right, the graph's going to grow. When we have a base that's between 0 and 1, that's called decay, right? Exponential decay. So the graph will fall as we go left to right. And again, the initial value, the value when x is 0, in both cases is a. So if we look at these first couple, right, we just want to look at is this growth or decay? And so in all these, we can really just check the base, right? So this one will be decay. Again, 0.6 is less than 1. In number 2, we've got growth because 7 over 5 is bigger than 1. This is decay. This is growth. Okay? So with exponential functions, right, they are always going to be increasing. Right, that's like growth. Or they're always decreasing. That's the same thing as decay. Okay? And when we say that, that means that there are no maxes or mins, right? So no extrema, unless, right, we have a closed interval, and so you don't have the whole graph. The ones that we're looking at right here, up above, these are concave up. Okay, so the concavity will not change. So these are always concave up. That's I'm drawing here the ones that we've got listed or drawn above. If we had a negative a value, they could be concave down. Okay, so if we had a negative a value, basically I'm gonna put that here. If a is less than 0, we could have graphs that look like that. Okay, but that's only going to be when we have negative values. In application problems especially, it doesn't really make much sense to do that. And so what that means is we don't have any inflection points, right? There's no points of inflection on exponential graphs. Let me write inflection points. No inflection points. Okay, so what that means also is for our end behavior, either we have the limit as x goes to infinity of a function is going to equal either infinity or it's going to equal 0, right? The case for infinity, right, x going to infinity, and the graph would be going to infinity. This would be growth, right? As we go to the right, as we move to the right, the y values increase, okay? When would the limit as x goes to infinity equal 0? Well, that's if we have decay, right? As we go further and further to the right, these y values, the function values, approach 0. And then the same thing could be said for going to negative infinity. The limit as x goes to negative infinity of f of x. So I'm going to do this in reverse. So these two are related, right? If we have a case where as x goes to infinity, the y values go to 0, that looks like this graph up top right here. And so that would mean that as we go to negative infinity, right? As we go to negative infinity, the function values go to infinity because we have this starting value being high, and as we decay, our values get less and less. So hopefully that makes sense. Maybe it's too much just kind of general properties, but that's it for page 1. Okay, page 2. Now we're kind of shifting into graphical transformations, so hopefully this will be a little bit more of a review. If we have a plus k, guys, right, next to the x value, then this is equivalent to a shift, right? A shift k units left. Shift k units left. Okay? Yeah. So if we look at this example below, right, we were starting with y equals 2 to the x. If we put a plus 3 next to the x, we can look at original points, right? The original value, let's pick, for example, 3, right? So on this original, when x is 3, we know that y is going to equal 8. Y is going to equal 8. And so I think, is that plotted? Let me see if I can make this a little bit bigger. 1, 2, 3, 4, 5, 6, 7, 8, 3. Yeah, so right there. Okay, and on the original, 1, 2, 3, 4, 5, 6, 7, 8. Looks like it's right there. Okay? So blue's the original. This new one, if we put a plus 3 there, well, basically now that's going to shift the graph 3 to the left. Okay? And so we can hopefully see that this new point, what was originally 3, 8, has moved to 0, 8. Okay? And I think I mentioned this before, but you can think of it as, well, if the original y value was 3, right? And I've got a plus 3, well, my new y value has to be, sorry, x values, guys. Sorry, x values. If my original x value was 3, and I put a plus 3 in the formula, well, now my new x value has to be 0 to match that original 3. That's why we're looking at, common y's, different x's. Okay? For a vertical dilation, right, that's going to be if we have some number out in front, right, multiplying the original function. Okay, so in this case, right, this 8, this is a vertical stretch, okay, by, I'm going to write a factor of 8. So this formulaic change affects the y values. So if we look at original, let's take the original point, let's mark that, and let's say that we know should be 0, 1, right? Because when x is 0, 2 to the 0 is 1. Now we've got that 8 in front, so that 1's going to get multiplied, 2, 3, 4, 2, 3, 4, 5, 6, 7, 8. Okay, so the new point here, the new point is going to be 0, 8. Okay, so we can do a horizontal translation by adding or subtracting next to x. we can do a vertical stretch or dilation by multiplying the whole expression by some number. All right, horizontal dilation. Well, yeah, I forgot to erase this, so I'll just keep it, okay? But basically what happens here is we've got a stretch by 1 over c. Okay? And another thing you could say is you could say it's like, I'm going to say a change of base. We'll look at that in a second. Change of base. But if you just want to think about it graphically, you can think of a stretch by 1 over c, right? It's a little confusing. Multiply by c, the graph will get stretched by 1 over c. Okay? So again, if we look at 2 to the x, and now we have a 3. So we have the x value being multiplied by 3. Okay, one way to think about this, guys, is this is going to be a horizontal stretch by 1 over 3. Okay, so for example, let's take the point 3, 8, right? That's what we had here. 3. Maybe it's not a good example, but it's okay. I'm trying to think if we can find a better example. Yeah, maybe let's just do, I don't know if it's going to show better, but let's do the point. This point is 1, 2. 1, 2. Well, now what I'm arguing is if we do a horizontal stretch by 1 over 3, the point should be 1 over 3, 2, right? Because we started with, try and show you here, we started with 1, 2, and now we've moved that, we've multiplied the x value by 1 over 3. Okay, so hopefully that makes sense. So yeah, we've got this one here was our original point 1 over 2. What am I doing? Not 1 over 2. Holy cow. It was 1, 2, and now this new point is 1 over 3, 2. Okay? So that's one way to think about it. All the x values, right? All the x values on the original, this blue graph, they get multiplied by 1/3. The y values stay the same. Okay? The other way you could see it is, well, if we do some algebra here, right? 2 to the 3x is actually the same thing as 2 cubed to the x. We can write it that way, and that 2 cubed becomes an 8. Okay? And then, right, if you want to get a nice clean 2, 8 to what power is equal to 2? Well, x is going to be the 1/3 power, because 2 raised to the 3rd power is equal to 8. Okay? So again, this is going to create the point 1/3, 2, which is the exact same, sorry, I wanted to go a different color there, which is the exact same point that we got over here. Okay, so hopefully that makes sense. One more page. What happens if we take the kth root of b? Okay, so fractional exponents, right? So it's just a notation, okay? B to the 1 over k is the exact same thing as the kth root of b. So for example, if we have 100, no, let's do 16, right? 16 raised to the 1/4 power. Well, that's the same thing as the 4th root of 16. And the answer to both of those is 2, because 2 to the 4th is equal to 16. Okay, so if we write this notation, we want to know what number do I have to raise to the 4th power to get 16? Same thing here. Okay, so if we look at transformations now in this example 6, we're starting with 3 to the x. Okay, this is going to be hopefully pretty quick. This is a vertical stretch by a factor of 9. Vertical stretch by a factor of 9. Here, well, this is like 3 to the x over 3 to the negative 3. So that's like 3 to the x times 3 to the positive 3, if I move it up to the top. And that's like 3 to the x plus 3. So actually, maybe that's too much to do. Maybe you're just like, why are you doing that, Mr. Papaduke? But so one way to think about it is, this is a shift 3 units left. Or you could just say it's a vertical stretch. That's maybe easier. Vertical stretch by factor of 1 over 27. And what I would encourage you to do, guys, is you could graph this in Desmos, right? Graph 3 to the x in Desmos, graph 3 to the x over 27, and you can see it. It should be the same thing as x plus 3, but now I'm thinking, why did I do that? To negative 3. No, sorry. Guys, let's make this a little bit better. Okay? Let's fix it. Originally, here's the problem, guys. Originally, this should be a positive, which means this should be a negative, which means that plus should be a negative. Okay? Hopefully that makes sense. So I don't know. I had 27 in the bottom. That's the same as 3 cubed. When I move it to the top, now I make that negative, that exponent negative, and that turns to this. So it's not 3 units to the left. It's 3 units right. Okay? But you should be able to graph, 3 to the x minus 3 on Desmos and 3x over 27 on Desmos, and it should give the exact same thing. Okay? So this last one, very similar, right? We have, I'm just going to write it as a vertical stretch by a factor of 1 over 9. Okay? So this is a vertical stretch because we don't know the common exponent, right? We can't, like we did here, convert the 27 to base 3 and combine it with here. We don't know what f of x is. So this third one is a vertical stretch by a factor of 1 over 9. Well, 9, in this case, 9 is 3 squared to the x. So we have 3 to the x changing to 3 to the 2x. So this is a horizontal compression. A horizontal compression. Sorry, I'm saying compression, but I just wanted to say stretch so we use consistent language. So compression by 2 is the same thing as a horizontal stretch by a half. I'm going to use that. And what does this do? Well, this means that g of x is equal to 1 over f of x to the negative 3. So this is this is a flip about the y-axis. So f of x is 3 of x, sorry. So this still applies here, guys. But I guess we could now say, let's do this a second way. So if this is 3 to the x over 3 squared, this could also be a shift right by 2 units. Okay? Very similar way that when we had a 27 in the bottom, we wrote it as 3 to the negative 3. We could write this. Let me do it here. Just so you're like, let's make it as clear as you can, please, Mr. Papaduke. I'm trying, right? So dividing by 3 squared, we could write that as, maybe I need one more step, 3 to the x times 3 to the negative 2. Then that becomes 3 to the x minus 2, so it's going to be a shift right. So it could be either of these two. Okay? So this last one, yeah, let me just change the notation, write it cleaner. Okay? So that is going to be the same thing as 3 to the x raised to the negative 3, which is 3 to the negative 3x. So this is a reflection, or actually, yeah. Yeah, let's just make it all in one, okay? This is a horizontal stretch by, gosh darn it, by negative 3 flipped. Sorry guys, I'm just kind of fading here. Okay, horizontal stretch by negative 3, or we could say a reflection, right? That's option 1, or it's a reflection. This is option 1, op 1. Reflection about the line x equals 0, so it'll be a vertical line, right? And then a horizontal stretch by 1/3. Whoo, that's option 2. Option 2. Okay, last one, guys, and then probably I'll make a second video going back and looking at these because we're getting to critical time here. This is a long video, so I want to stop it before doing a second one. Okay, so evaluate the functions of the given input values. All right, this is pretty easy. So we want h of 1. So h of 1 is going to equal 2 times 5 to the 1/2. That's going to be 2 times square root of 5, right? That's all we can do. And then here, we want h of negative 2. That's going to be 6 times 2 to the negative 2/3. Right, that's the same thing as 6/2 raised to the 2/3 power, which would be 6/4 to the 1/3 power. So I don't really, I mean, we could write it like that. We could write it as 3rd root of 4. There's another way we could write it, but I'll stop it there. Okay, so hope that was useful. Really, really hoping that the audio works on this now. I'm going to be really mad if it doesn't. But I'll make a second video going up on these, or going through these exponential regression questions in a second here.